Hey everyone, we're going to go ahead and do the hydrology demo today. I've already gone ahead and done the new project file and loaded up ArcGIS Pro in the background. So it's a little bit different here that you can see some of the other things that are in here. But if you notice right away, the files that are new in here are basically this SRTM, which is what we downloaded before. It's just been repackaged. I'm going to use that for the demo. You should probably use it for your the first part of the demo at least. And then also this eRisk DBF file down here. This is just something you're going to use as part of the assignment. All right, so to get started, we're going to go back over into ArcGIS. And we're going to try to remember the overview of hydrological modeling, a surface hydrological modeling that we use. We're going to first look at a DEM for sinks. We're going to fill those sinks. We're going to create a flow direction and a flow accumulation from a sinkless DEM. We're going to calculate stream order. We're going to do a few other things as well, stream to features, and we're going to do some of those pour points and watersheds. We can kind of divide that up into two big sections. The first thing we're going to do is a stream network across the entire surface. And then second, we're going to measure flow at particular points. So these are a couple of things that we're going to definitely want to do. You can go ahead and just add in those two layers that I gave before. If you have a catalog window open, you could just use that. It's going to be hopefully in your Lab 9 hydrology folder, that SRTM, and then that DBF. You don't have to add the DBF right now. So when that eventually loads up, well, that's taking a minute. There it goes. What you notice is that it is that it's a slightly cut down version of that DEM that SRTM DEM that we downloaded before, and then the standalone table down at the bottom there. You can just ignore that for right now. So as you can see, it's the area that we want. It kind of covers everything. The reason why we're not doing this for the individual parks, and I want you to do it for the whole area, is what we talked about in the demo or in the lecture, that doing hydrological modeling, you usually want to go bigger because you could miss things around the edge. There'll come a point later on when we do this, and you'll notice that this is the St. Joseph River right here, and it's not going to look like a river because in order for this part right here to look like a river, it has to catch a whole bunch of topography that's outside of the image. So by doing this bigger area than the individual parks, it gives us more of what we want to be working with. So I'm going to change this to be a color scheme that is something that looks like topography to me. So you can choose one of these elevations. And you can see that it's SRTM data, so it's not, it's a little wonky. It picks up things like roads and some buildings and stuff, but that's okay. We just aren't going to be doing a lot of things on individual buildings. So first step we want to do is this flow direction. And if you remember, the flow direction is really pretty cool because it has this binary or this powers of 2 encoding, so it can handle uncertainty as well. So it goes 1, 2, 4, 6, 16. It's 1, 2, 4, 8, 16, 32, 64, 128. That lets it tell you when it can't decide, when it can't figure out between different ones. And that's usually because of sinks. So we're going to run this first. We're going to do these. Most of these things can be found a couple of different places. I'm going to go into analysis and do tools. And I could just search for flow direction in here. But if I come over to toolboxes, it might be useful for y'all to see that these are all in the same spot. Spatial analysis, hydrology. So almost everything we're going to be doing is in this section right here. There's one section where we'll do something that's not right in there, but that's okay. So you could either search for the tool, or you could just do the flow direction right here. I'm going to just do it right here. Flow direction. I'm going to bring in my SRTM Michiana. And I'm going to keep this one as a permanent file instead of dumping it into my database. You can do it however, if you want to put it in the database, that's fine, but I'm just going to go into folders. And I'm going to call it flow, I'm actually going to go back and do Michiana flow direction. And if I put .tif on it, it knows to do it as an independent file. You could do flow force all edge tells to flow outward. You could do drop raster if you want to. You don't need either one of these right now. This flow direction type, there's different methods for doing it. We're going to stick with this D8 one. That's a directional 8 around the center one. So go ahead and hit run. It'll run for a minute, and you'll end up with something that looks like this. So it goes from 1 to 255. And remember that there's a lot of uncertainty in these things because of the sinks, which you can kind of see are some of the lakes that are in there. That's the Lake and Potato Creek. We have quite a lot of uncertainty in here. So what we want to do first is to fill those sinks. I talked about this a little bit in the lecture, but filling sinks, it seems like it's a bad idea because there are places where water naturally accumulates, rivers, lakes, that kind of stuff. But generally, eventually, it will flow back out of there. So even if there is a little gullet or something, you want to be able to model what happens afterwards, because that thing can't infinitely be filled with water. So to do a complete stream network, you have to fill in the sinks. So I'm going back to my geoprocessing tools. You could search as well. I'm going to run the sync command right here. What the sync command will do was identify all of those sinks so I can see how many there are. So input D8 flow direction raster. That's my Michiana flow direction. Just to show you can do this, I'm going to drag it over. Our output, you could make it, permanent if you wanted to. I'm going to call it Michiana sinks, which sounds like a store, but that's fine. .tif. And when I hit run on this, what you'll see is there's actually 12,646 spots on that image where water flows into and not back out. That's pretty common from satellite imagery stuff because it's sort of taking an average of the area right there. Sometimes it can be a little lower than it needs to be. Sometimes it can be a little higher than it needs to be. So often with satellite imagery, you'll have a pretty high number of sinks. If you notice it's colored just from the 1 to 250 to 12,646 here, that's just the number, the idea of it, and it kind of starts at the bottom and works its way up to the top, which is why, or starts at the top and works its way back to the bottom, which is why they kind of grades and grays down there. You could turn that off if you wanted to, but we're only using these to see where they are. So I'm gonna leave those as is. Now, because we have all of these sinks in here, the next thing we want to do, we could do this manually. Some of them we might want to keep, some of them we don't. Some of the things we want to deal with, but in this case, we're just going to fill them all in. And this is probably the most common thing you do with sinks, is just fill them all in so you get a surface hydrology model, even if some of them are natural lakes and things like that. So I'm going to go up to fill here. I'm going to run this command called fill. It's not asking me for the sinks. It's asking me for the surface raster. In this case, the surface raster is the DEM, SRTM, Michiana. You definitely want to save this one permanently because you're going to keep using it a lot. So if you haven't been doing this, go into folders instead of databases. I'm going to call this, I don't know why I'm spitting it out. I must have accidentally sent these into the modeling folder. Just ignore that and send it into the correct one. Call it Michiana DEM fill.tif. You could call it SRATM Michiana fill if you wanted to, just for comparison. So I'm going to run this, and then I'm going to change my symbology just to match the other one as well. So if that was at elevation 1, just make sure that they're the same one. Because what I want y'all to do a little bit is compare what's happened between them. So I've got one on and the other one here. I can either just sort of click them on and off, or I could go over into that swipe tool and sort of pull one off of the other. So you can see what's happened is there's lots of places in there where there were low things that have been raised up. Those were spots that water flowed into and couldn't flow back out of. Like I said, some of those are lakes and are probably accurate. Some of them are not. And even if they are lakes, water will come back out of them. They're not infinite basins. So this is the sort of base layer that we're going to use from hydrology. It's a process DEM to make sure that water flows continuously across the entire thing. So now we're going to take a step back, going back to my geoprocessing, and I'm going to run that flow direction again right here. So I'm going to go to flow direction. This time, my surface raster is going to be the filled one, Michiana DEM fill. And I'm going to save this output as somehow. I'm going to go back into the right place. Sometimes it was going to one folder, sometimes it was going to another. I'm going to call this Michiana flow direction, but I'm going to append filled on it as well. And this is the one that we're going to keep using throughout. So I'm doing the exact same thing over again so that I can compare what my flow direction originally was with my filled flow direction. And what you'll probably notice right away is that this looks like something you should have under a black light, because it looks a lot like an aspect as well. Because when we fill those things in, it no longer has ambiguous areas. It no longer has areas where it can't figure out if the flow direction is to the east or to the southeast, because there's water collecting in there. It doesn't need to worry about that anymore. It can figure out every single pixel and how water is going to flow from it into the next one, into the next one, into the next one. So what we've done is created this nice, just 1 through 128 by powers of 2 image that we're going to use to then do all of our surface hydrology afterwards. So our next step is a flow accumulation. So again, it's down in here. You could also search for it, flow accumulation. And this is going to tell us how many pixels flow into each spot. It gives us an idea of how much water is upstream of any place that we're dealing with. Flow direction raster is flow direction fill. I would not try to give it the raw one. It's not going to work very well. And then we're going to do Michiana flow ac.tiff. I don't have a clever thing for that one. You could leave it. However, you could do some of these other ones if you wanted, weight rasters, these sorts of things. Just leave it all as. It's fine. It's not a big deal. We did bring it in as a D8, so we want to keep using that. So go ahead and hit run. And what you'll see is this one takes a little bit longer to run generally because it's calculating backwards from every single pixel in the image. Hopefully it's not going to take a very, very long time. But when it does come out, what it's going to look like is kind of a stream raster. You can see the St. Joseph River roughly in there in kind of its northern part. You can see the Kankakee over here as well. You can see some of these other little spots because those are spots where there's 30,000 pixels upstream flowing through, and then there's spots where there's 0. This is not a super useful way to look at it. We probably, as hydrologists, surface hydrologists here, we probably don't care particularly much about the spots that only have 1 or 2 or 3 or 5 or 500 pixels flowing through them. So what we can do when we have something like this is right now, this isn't a very useful way to look at it. We've got all of this stuff in the way. I'm going to change it just so I can see what's happening a little bit more. There's so many low values that the high values aren't seen. I'm coming into the symbology. The percent clip on here is not useful. I'm going to go to a standard deviation instead. Right now it's at a 2 standard deviation. You can start to see it looks more like hydrology. You could actually change that to be a little bit smaller if you want, 0.25. Then you start to see something that looks kind of like a stream network. But to create that stream raster, what we actually do is what's called a threshold on the image. So we're going to remove all of the low pixel values in here and then say, give me just the high pixel values. Make the high pixel values a 1, make the low pixel values a 0. That is, if it sounds like what you've heard about before, actually make them a no data, not even a 0. What we talked about before, this is a reclassification, and that is one way to do it. In this case, we're going to, for this image, and this is not standard for every single image for you do hydrology on, we're going to throw out any pixel, we're going to delete any pixel that has less than 50, a value of 50. That means upstream of it, there's less than 50 pixels that flow into it. That is actually around 4,000 or 45,000 square meters. So it's actually a pretty big area, even on 50 pixels. And if you were to look at the histogram here, you can see that that's the overwhelming majority of the things that are in here are low. So it's actually going to toss out quite a bit. So we have 2 ways to do this. The first is to run a tool called the con tool. And the second is to do just a reclassification. So I'm just going to go ahead and start off by doing a reclassification for you. The reclassification, again, if you remember, it's just the reclassify tool. We would bring in flow accumulation. When you're doing this, just choose one of these. Don't choose both of them. I don't do both of them. The reclassify field is the value. I'm going to go classify. I'm going to do 2 classes here. I'm going to put the upper value on the first class is 50. Sometimes people run into an issue where if they do this wrong, they end up with it doesn't catch every single one. It actually only looks at like 75% of the pixels in the image to get these numbers. So it might the 75 was a complete fabrication. I don't know what number, it doesn't look at all of them. Sometimes it's useful to just take this right here and just add an extra 0 onto the end of it. Chances of there being pixels that are outside of that are pretty low. So you're probably fine there. And you're going to end up with something where you have 0 to 50 as, right now it's a 1, and 50 to everything else as a 2. We want to change these to remove these low pixels. So we're going to do no data. And we want to keep the high pixels as a 1. So I'm going to then browse here. And I'm going to save this. I don't know why it keeps going into my modeling folder. I'm going to save this as Michiana stream raster. I'm going to call it 0, 1 just because I'm going to do the other way too. But .tif. Again, remember, you don't have to do both of these ways. If I spelled anything in there right, it would be useful. I'm going to hit Michiana stream raster 1. Go ahead and hit OK. And then you could change the missing values to no data. That would actually solve this problem up here, but you'd lose some of the bigger values. So it's better to do it that way. Hit run. And what I end up with is somehow I kept my 2s in there. That should have been a 1. I must have undone something or something. So it's warning me right now that exists, but I can actually just hit run and it'll overwrite it. Why does it keep doing that? Okay. There we go. Now it's a 0. That's 1. So if you end up with something where you have higher values than this, that just means you needed to put another 0 on the end right there. So doing just the 1 is totally okay. That's what you want. Now I know this probably seems a little counterintuitive because now you suddenly have something where you're not, you've lost like how big they are. When you do stream networks, you actually recalculate that afterwards. That's something that is based off of the number of channels that come together more than it's based off of the amount of water flowing through them. So flow accumulation can be useful for things like figuring out how many, like what is the drainage area above something. But honestly, the stream rasters is the way that this is kind of done, even though it seems like you're losing some data that are in there. So the second way we can do this stream raster is to go to the raster calculator. So you can search for it. What you're going to do is you're going to bring in a tool. If you scroll all the way down here, there's a tool called Con. You could also just type this in. Con is a tool that if I give it a raster, and then I also give it a condition. So any place where Michiana stream raster 0. Oh, sorry, that's the wrong file. I want to give it the flow accumulation. So I'm just going to delete that real quick and go to flow accumulation. I'm going back before the comma because I also want to say flow accumulation is greater than 50. So what it's going to do is look at every single pixel in there, and if it's greater than 50, the next value that it gets is what it's going to give it. So I'll give it a 1. So it says if it's greater than 50, give it a 1. If it's less than 50, just delete it. You could specify a no data afterwards, but in this case, it'll do it automatically for you. I'm going to come in here to my files. And remember, I'm just going to call this stream raster 2. They should be exactly identical, just 2 different ways. Just wanted y'all to see a different way to do some of this raster calculation because it can be kind of useful. I mean, they come in with different colors, but they're fine. The advantage of the second one here is that it's a piece of code that you can copy and share. It's not just a tool you're running. And also, you don't run into that problem where if it doesn't doesn't know that there's higher pixels in there, that it'll do something different about it because it's just comparing them against it. So I like the second one, but you can do whichever one you want. All right. So at this point, we have a stream raster. What we want to do is order that stream raster. If we go back into our hydrology tools, there's this stream order tool right here. This is a smart thing that will do this in a slightly better way than if we just tried to convert it as it was. So we're going to come in, it wants a stream raster, it wants a flow direction raster, and it wants an output. Then there are these two different methods, Strahler and Shreve. You can do either ones. I usually just use the Strahler. It makes a little bit more intuitive sense to me. So our stream raster, I'll do two. Doesn't matter, we'd use whichever one. Flow direction is definitely wants to be the flow direction filled. And I'm going to call it Michiana stream order .tiff. And when I run this, now I have low classified streams to high classified streams. With the background map in here, you can't see it super well. If you start zooming in, you can see that these things actually are, when the pyramids start building, you can see that, so this right here is a 7, which is built out of whatever this one is, whatever that one is. There's some 5s back here. It's built off of the number of things upstream of it. So there's some 1s are the really, really basic ones. They feed into 2s. Those feed into 3s. They feed into 4s. I don't think I can see all of the places where it would feed in numerically just because the river itself is so big. Okay. If you have all 1s, then something went wrong. Just make sure that you look at the lecture notes or the demo notes. They've got them in there. So this is raster data that looks like vector data. We probably want to convert it into vector data to be able to look at these things. There's a tool for that too. It's called Stream to Feature. This just does a smarter, better job of doing this than if we just did it by converting directly. It's smart. It figures out how to do streams a little bit more accurately off of the pixels. So stream raster, I'm going to give it a stream order. Flow direction raster, I'm going to give it is flow direction fill. My output stream polylines. You can give it. You can make it. I'm gonna make mine as an independent shapefile, but you could do it in the database if you wanted to. You may use these again. There's some useful spots later on, and I'm gonna call it Michiana. So I'm gonna call it. It's called stream to raster. It's called streams. These sorts of things. I like to think about them as drainage paths because these are not streams in the sense that there's water there all the time. This is just how water is going to collect and flow. And we've all seen this if we've looked at a landscape as it's raining really hard. So I always call these Michiana drainage paths. You can say simplify is fine. So what you'll end up with is this nice thing where we're going to have a shapefile that shows these drainage paths instead of this sort of rasterized data here. Just coming back over here to this. So once this finishes, which it might take a minute or two because it's got some math to do behind the scenes, we can start kind of leaving behind the idea of looking at the entirety of the image and start thinking about how we would look at individual points and kind of what happens at individual points. Another thing you want to do right at the end here is take your drainage paths, come over into the symbology. We're going to go back to change it from single symbol to graduated symbols. Personally, I'm not a huge fan of calling my things, my water yellow or showing my water as yellow. You do want to change it as the grid code. So it's going to go from 1 to 7. I would say it probably makes sense to just make that 7 classes. And I would hit the template here to change this over to being under properties, maybe a little bit blue, perhaps. Apply. And now when we start looking at it, what you'll see is you've got, your little ones feed into your bigger ones, feed into your bigger ones. Looks like a nice drainage path. As I've talked about before, the river gets a little bit messed up because it doesn't have as much flowing into it as you would expect from over here. Catches the Kankakee pretty well. But the St. Joseph, it's just there's stuff up here that would flow into there that would make this a bigger drainage path, but it's pretty good everywhere else. So we successfully remade a river as the bigger parts, and then you can kind of see if you look at it against the DEM why water flows in certain ways. I'm going to turn off some of these other rasters that are in there. You can see why. So right in here, this is, water's flowing down through this kind of channel here off to the side and kind of coming down that way. So this is sort of the last stage of creating the whole image. Now we want to look at individual spots. I'm going to ask y'all just to make sure at this point that you turn off the drainage paths. There's a point where we're going to create some locations for drainages, and if the drainage paths are on, it kind of over, like they're already where they need to be. So just do that for me. Maybe to suspend your disbelief and just trust me that it can be a better surprise if you do it that way. So the next tool we can run, if we go back into our toolbox, is what's called the flow length. Flow length is just going to say, instead of looking at the entire surface, it's looking at individual pixels and saying, from this pixel, how far do I have to go to leave the image? This is not a tool I use a whole lot, but there are some cases where it could be about sort of how long water is going to stay in a park or something like that. So if there's a spill, a chemical spill, how long is it going to be before it gets out of there? So there's some times when you would use this tool, and it's probably useful to think about it. So it wants the flow direction. It's kind of the opposite of the flow accumulation in a lot of ways. So we're going to go to our flow direction is filled. We call it flow length Michiana. Again, you could say this is permanent. This is not one I use a lot. Again, floater. Oh, sorry. This is not, that's flow length. There's upstream, downstream sections here. You can choose whichever one you want. It's not dramatically different. I'm just going to leave it on downstream. So now what we have is, so like I said, it's kind of the opposite of flow accumulation. Areas where not much accumulates, but it takes a really long time to get out look like this. If I turn on my drainage paths over it, you can see why. So the stuff from right here has to go all the way down, all the way off like that. Something from right here just has to go that far. Something from the edge just has to go a little bit, which is why those are lower values. All in all, tends to look very similar to the stream raster. Another one that we often do is this tool called basins. And what basins do is it's basically saying it's going to divide the entire area up into different watersheds. So it's based off of all the spots around the outside where water could leave. What is the upstream area for each one of those? So if we run the basin tool here, it wants a flow direction. Michiana flow direction filled. I'm going to call it Michiana Basins. That's the satellite store for Michiana sinks. It's actually downstairs. Haha. Oh, I sent it. Sorry, I sent it. So this is, if you see this happen, I started to send it into the databases instead of the folders. Run that. And you'll see that there's some big basins in there. And if you look at the drainage paths, you can kind of see why. But then there's 1,600 of these in here. So there's a lot that are just little ones right around the edges. And that's kind of what we're seeing. If you look over here, over down in here, there's some spots that are just really, really small ones. Okay. But what often you're more interested in is not the water catchment area, the basin across the entire area. But what you're more interested in tends to be what flows through particular spots. And the way that we do that is a tool called watersheds in ArcGIS, in sort of the hydrology workflow in ArcGIS. And these watersheds are going to take points, either from a vector or raster file format, and use them to create these sort of upstream view of stuff. So the first step to doing this is we're going to create a new raster, new vector shapefile that is the points that we want to look at. This is where I was saying to make sure your drainage paths are off, because otherwise you'll end up with a situation where you've got it on. It's automatically catching what it should. So I'm going to go into the catalog window. If you haven't done this in a minute, I'm going to go over here, right click on the hydrology folder, new shapefile. I'm going to call this shapefile Michiana pour points. I want to make sure my geometry is a point. I want to go down and make sure I set a coordinate system. You could go to favorites if you have it set. You could also go to layers and just make sure, because one of these should be UTM zone 16 north. Go ahead and hit run. Got this new blank shapefile now. What I want to do is go over to edit, create pour points, and I'm just going to put kind of 10 random points throughout here. You could do 10, 15, however you want to. So I'm going to do one up there. I'm going to do one on the Kankakee, try to catch one in here, right in here. I'm just going to put some sort of random points throughout. It's probably more than 10, but so once I've put my points down, I want to give them an ID. That's the only other thing I really need to do. So I'm going to open up my attribute table. Yeah, I did 12. That's fine. It has the FID, but I'm going to just in the ID field, I just want to go through and do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to hit save. And then just because that last feature is selected by default, I'm going to hit the clear selection button right there. If you don't do it, there's one more step you have to do later on. All right. So now I want to calculate the basin, the watershed upstream of each one of those points to sort of see what that area looks like. I go back into my geoprocessing tools. If I have to go back up, I can. It always sends me back over the catalog, but it does. Watershed is the tool I'm going to run. My flow direction raster is going to be Michiana flow direction fill. My input raster or feature pour point data. That's those pour points that I created. Michiana pour points. The ID is what I just set for it. I'm going to give it an output. I'm going to make mine permanent over in Hydrology. And I'm going to call it Michiana watersheds raw .tif. I'm going to run it. And you'll notice immediately that yours may not look like this because you may not have caught the points particularly well. That there's some spots where I caught, an area that a significant amount flows upstream from through that point. But others where, this is in the middle of the St. Joseph River, but just because the pixel where it flows through, because the way that these things work is it's a single pixel wide, it's not probably particularly realistic. It probably is a much bigger area there. So I want to find a way to be able to figure out what is probably more realistic than accurate for these basins that are upstream. And that's this tool that they have in there that's going to move them to the place within a certain radius that has the highest amount nearby. And it's called snap pour points right here. So I'm going to give it my pour point data, Michiana pour points. Pour point field is the same. My flow accumulation raster. So flow accumulation instead of flow direction here. Flow accumulation, I'm going to give it an output of, I'm going to go back into folders. This is a raster layer, strangely, even though it's going to be individual points. It's just how it works better for the raster calculator behind the scenes. I'm going to call it Michiana pour points snapped.tif. And then the snap distance here, this is the number of meters in this case away from each point it can move. This is this is the number of pixels away from each one it can move. In this case, this is a 30-meter resolution image. So I'm going to say it can move 10 pixels away. That's completely fine with me. Oh no, it is map units now. Sorry, they switched it around, so it's map units now. So I'm going to go out to 100 meters or 300 meters. That's 10 pixels. That seems about relevant to me. So 10 pixels is probably fine. So 300. If you look real closely, you can probably see that it's moved the point, but it's just made it a little blue square right there. So that's the new layer right here. So it's an entire raster image where the only pixel value that's happening in there is the individual point. So there's a whole lot of no data, and then there's 12 pixels that are coded as 1 through 12. So once I have that, I'm going to go back over. I'm going to run my watersheds. I'm going to give it my flow direction raster, Michiana flow direction fill, my raster or feature pour point data. That's the new one, pour point snapped. put this here. I'm going to call it, just like I did before, Michiana Watersheds Raw. I'm going to call it Michiana Watersheds Fill. There's one last setting that I didn't do before because it's not as relevant, but I do want to do it. I'm going to go over in environments. I'm going to choose my processing extent here. And in the dropdown, I'm going to make it the same as just like the DEM or one of the other ones. That just keeps it from not going out far enough based off of the points. So I'm going to hit run. Now I have something that is probably more accurate. So this point right here hits the Kankakee, gets the whole upstream of it. This point right here gets the St. Joseph River, it gets the whole kind of upstream of it probably. Obviously it would come more in this direction too. The ones sort of upstream of here, inside of here, are catching smaller areas, but they're sort of part of the bigger one. So what we can see is that we've created these nice big images that are going to show us the spots that are likely to flow backwards through that. Snapping them can be a much more realistic way to do it and can kind of be a nice surprise here. So when it comes time for assignment, you're going to do this sort of stuff, mostly doing this. There is a part of the assignment as well, if you look at it, where you're doing a more intense version of this, where you're actually going to create your own analysis. That's why this is a two-part assignment as well. So you're going to do a model based off of the hydrology, but rather than just doing the step-by-step following the hydrology along. So good luck. Let me know if you have any questions. And yeah.